We're going to continue our discussion about infiltration by considering a fairly old model for infiltration and a fairly simple one. And this is by no means the only model for infiltration that exists in the literature. There's many others that we can study, and some are in the textbook. But this one is illustrative and gets at a lot of key points and also allows us to exercise a little bit of our mathematical minds in the process. So in 1933, Robert Horton was doing some experiments and observed that for any particular soil, the maximum rate at which water can soak into the ground, the infiltration capacity, denoted F sub p, tends to decrease exponentially from some initial rate or initial capacity, F sub 0, to some long-term steady equilibrium capacity, F sub c. And so if you're watching at home, I'm going to give you a few tasks and then ask you to pause the video and do these on your own. One, I want you to draw a plot depicting what is said in words here. Two, I want you to derive a simple equation in which F sub p as a function of time on the y-axis is plotted against time. And then three, I want you to think of some mechanisms or processes that might explain why this behavior actually happens the way it does. So pause the video and work on these. And when you're ready, we'll come back to do it. So let's draw the plot. Well, we know that it starts at some initial capacity F sub 0. So let me first label my axes. This here is F sub p. It has dimensions of length for time. It's an infiltration capacity. I'll label that here, infiltration capacity. And then this axis here will be time. T, dimensions of time. All right. What do we know? Well, we know that it's going to start at some rate F sub 0, and then it says it will decrease exponentially to some equilibrium capacity F sub c. So here is the equilibrium capacity. What does a decreasing exponential function look like? It decreases most rapidly in the beginning, and then the rate of decrease tends to slow down. So if I were to just kind of project this horizontally over here, we would see something like this. So this is at time t equals 0. So this is part 1. Draw the plot. Part 2, derive an equation. Let's review some of the things that we know about exponential functions and just talk about the way that this graph should behave in the limit. So I know that at time equals 0, this function f sub p had better be equal to f naught, or f sub 0. I know that in the limit, and I'll depict that as time goes to infinity, it had better reach the equilibrium capacity, f sub c. I also know that this function in general should scale like a negative exponential, e to the negative kt. Another way of writing that would be 1 over e to the kt. I also know that in general, if I put in t equals 0, this term is equal to 1. So a number to the power of 0 is equal to 1. And I know that if I were to, in the limit as I head towards infinity, this thing is going to approach 0 as well. So 1 over an increasingly large number, you're going to go to 0. So that should help me, putting this together, kind of describe what's going on here. So I know that in the limit, we need to get to f sub c. So I'm just going to throw this in here, and then I'm going to add on some other term here and put this other piece of the puzzle that I know has got to be in here, this other behavior in here. So if this is what it needs to get to when t is a really big number, and I know that when t is a really big number, this is going to go to 0, so that will behave no matter what I put in here. This is going to be the only thing left. What I need to do now is figure out at 0, when time is 0 and this is equal to 1, what do I need to put in here to make this entire expression equal to f sub 0? Well, I can just do something like this, f sub 0 minus f sub c. And if I do that, at time equals 0, this part's 1, so you're just multiplying by 1. You're going to cancel out those two f sub c's and the equation is going to behave. So finally, why? Well, there's a variety of mechanisms. They may vary in importance across different places. One is that clays may expand when they get wet or swell. So that's going to, as these clay molecules expand, it's going to decrease the pore sizes, so it's going to be harder for water to infiltrate. It may be the case that as water is flowing over the surface, there are fine sediments. And those sediments kind of fill the pore spaces between the bigger grains and cause it to clog. But one of the most important things is actually that there's a decline in capillary suction with time. And we're going to talk about this in a fair amount of detail further on in the class. But the general idea is that dry ground, like a dry paper towel, is going to try to suck up water. But as it gets wetter and wetter, that suction power decreases. And we're going to leave it at that for now. The main thing to take away is that this is a general form. There are definitely more complicated descriptions of infiltration, more nuanced, but this is a fairly useful framework for thinking about it. So just remember that it's this decreasing exponential function with time. This is how you would kind of work your way towards an analytical expression for this particular type of behavior, and these are some of the mechanisms that are responsible.